Go through example 5.2, abrupt stop in a car. It starts on page 159 and it continues on to page 180. And it starts like this. A 60-kilogram person is traveling in a car that is moving at 16 meters per second with respect to the ground when the car hits a barrier. The person is not wearing a seatbelt but is stopped by an airbag in a time interval of 0.20 seconds. Determine the average force that the airbag exerts on the person while stopping him. So, part of our sketch should include a person.
What if we calculated how much the wall would have flicked on him if there was no airbag? That'd be a lot of force. That would be very much force.
So there's my green person
Oh, yes.
driving the car. And here,
There has to be something wrong with you. Like, honestly.
Smuff, I don't know if you're at two.
Thinks or knows?
She just knows. She likes to self-diagnose people.
So the system is just going to be defined as the person. We're concerned about how the person is going to interact with this airbag. The mass of the person is going to be 60 kilograms. So we're going to probably want to put that in our picture. And the person's mass is not going to change. At least hopefully not. Our time up here, our initial time, is going to be 0 meters per second. Or not meters per second, just seconds. Duh. And our velocity initial in the x direction is 16 meters per second, going that way, toward the wall. Our final time is 0.20 seconds, provided by that airbag. Our final velocity in the x direction is going to be 0 meters per second.
That's slowing down pretty quick.
That is slowing down pretty quick.
I don't know. I might have some head injuries after that one.
And we're wondering, what is the average force?
Oh, wait, you should go back up for just a tad.
Sure. So I want to make a free body diagram of the forces on this person that they'd be experiencing. There would be some sort of an upward force. There'd be some sort of a downward force. Equal and opposite.
Yeah.
And in order to accelerate to the left or slow down, negative acceleration, there would have to be some sort of a force in the negative x direction. I'm going to label these as normal force of the seat on that person. We've got the force of the earth on that person. And we've got force of the bag on that person. I'm referring to the airbag. Why am I not using A? I don't know. The book uses bag, B for bag, on that person. That's true. So this is, we're going to be looking at the mass of the person, the velocity of the person initially in the x direction. It's a lot of stuff. Plus the force of the bag on that person in the x direction times the t final minus t initial.
Which is not a lot of time.
Nope. That's going to be equal to sort of the afterward situation. Mass of the person and velocity of person final in the x direction. What these three terms are is, and for whatever reason, P is also stands for momentum. So what this is the person's initial momentum. And what this is the person's final momentum. And if that's ever different, the only thing that can change momentum is something called an impulse. Of course, impulse starts with I, so the abbreviation for impulse is J.
Well, that makes sense.
What impulse essentially is force multiplied by a change in time. Basically, how much time that force is. Impulse. J for impulse, because of all the J's in that word. Force multiplied by the amount of time that force is being applied. So you can have the same impulse with a small force over a long period of time or a large force over a short period of time. You're going to have this, when you go and you stop, you're going to have the same impulse regardless, and I'll talk a little bit at the end why airbags work the way they do. So I want to get force by itself. That's what we're concerned with. So to do that, I'm going to subtract MP PIX, mass of person, velocity of person initially in the x direction from both sides. So that means this part cancels, and I'm left with force of the bag on that person in the x direction multiplied by final time minus initial time is going to give me, now I'm super confused. I'm not anymore. Mass of person, velocity of person, final in the x direction, minus mass of the person, velocity of the person initially in the x direction. What you may notice now is we could factor out MP from the two terms on the right. So I'm going to do that. MP, velocity of person final in the x direction, minus velocity of the person initially in the x direction. Over here, we're still going to have the same stuff. Force of bag on that person in the x direction, and then final time minus initial time. We want to get force by itself, and so we're going to want to divide by TF minus TI. That's supposed to be an F. Okay. Meaning that cancels. So I'm going to scroll down a little bit more. We end up with force of the bag on the person in the x direction is equal to mass of the person, velocity of the person final in the x direction, minus velocity of the person initially in the x direction, over T final minus T initial. Now we can actually put in numbers and get a value. The mass of the person is 60 kilograms. The velocity of the person final in the x direction is 0 meters per second. The initial was 16 meters per second. And then our final time was 0.20 seconds minus our initial time of 0 seconds. Force of bag on person in the x direction. This would give you a value of negative 4,800 newtons.
That's a lot of newtons.
The negative, because the force would be pointing to the left, what we define as the left. And if the force is pointing to the left, that's our negative x-axis. This would be roughly equivalent to 1,000 pounds
Whoa,
to the face.
that's real fancy.
Now, you're going to have the same impulse regardless. So if you don't use
No question.
an airbag, instead of taking 0.02 seconds to stop, you take 0.01 seconds to stop.
Oh my God,
You're-
you'd be gone.
Your
Oh, that thing
impulse is the same. Your change in time is a lot less, which means the force on that person ends up being a lot more.